So till where did we discuss yesterday? We saw about the phasor diagram, right? So we will see the next part of this chapter, that is what happens when you connect an AC source across different passive elements. Ah. Careful with your hand. You're taking close to that. Chair is okay. You're fine? That's in a bad the shape. So AC source connected across a resistor. Okay. Now see, if I have a resistor like this, across which we have connected an AC source, and the AC source has EMF of E0 sin omega t, then current starts flowing through this device. Right? Let's say the resistance is R, then the value of current I can write it as E divided by R, which will be equal to E0 sin omega t divided by R. This E0 divided by R, I can call it as I0. So E0 divided by R, I'll call it as I0 sin of omega t. So the meaning of this is, when you give an input voltage of E is equal to E0 sin omega t, you get an output value of current as I is equal to I0 sin omega t. Is that clear? Please make a note of this. Yeah. Right. Now, we will try to analyze the same thing using a phasor diagram and graphical representation. So when I talk about a phasor diagram, see, phasor diagram is not graph, okay, don't get confused. Phasor diagram is just x-axis and y-axis. Okay, where you take the rotating vectors x dash and y dash. Suppose this is the expression for, if this is the phasor for EMF, then EMF has got rotated through an angle of omega in time t. Sorry, has got rotated through an angle of omega into t. Then what about the current? So if you see current, this is where you need to be careful. If input argument was omega t, output is also omega t, meaning current would also have rotated through the same angle, except the fact that current will be slightly less compared to the value of EMF. So what I can do here is this will be equal to E naught sine omega t, and this will be equal to I naught sine omega t. Is the point clear? You will know when I explain capacitance. That point you will understand. Okay. So in this case, you can observe that EMF and current are in the same phase. Okay. Now, if I do the same thing, if I try to observe the graphical representation of it, if I take this as x and y, sorry, not x and y. If I take the x-axis as time and the y-axis to be EMF and current, means you are drawing both on the same graph. Okay. If I call the first sinusoidal wave as E naught sine omega t, then I can draw another sinusoidal graph which exactly follows the path of, sorry, which is exactly in phase with the EMF. Then this red color thing will be called as I naught sine omega t. This is called as E naught sine omega t. So from this we can conclude. So what they are asking your exam is, they'll give you a graph like this and say, this graph corresponds to which device? It corresponds to a resistor. Is it clear? So this is how it works. Okay. Next is, I hope those who are online are able to follow it.
Yes, sir.
Now the next point is about an AC source connected across a capacitor. It is only R. AC source connected across a resistor. No, no, no. It is not LR. It is only a resistive circuit. This is called as a purely resistive circuit. LR means inductor and resistor. So AC connected across a capacitor. So when I take a capacitor and connect it across an AC source. Okay, when I connect it across an AC source where the capacitance, I call it as C. Then what if I say the input value is E is equal to E naught sine omega t, then what is the amount of charge that will be stored on the capacitor? So charge on the capacitor is equal to, can I write it as C into E? So this will be equal to C into E naught into sine omega t. So Q is equal to C E sine omega t. So from Q, how do I find the current? I is equal to dq by dt. So if I do this, I get C into E naught into, yes, cos omega t into omega. Is it right? Yes. Because when this is the instantaneous charge, when you differentiate it with respect to time, you get instantaneous current. So I is equal to dq by dt, which is also equal to C into E naught into cos omega t into omega. So can I write this as omega into C into E naught sine omega t, which is I. So I will be equal to E naught divided by, can I write this omega, sorry, not sine, cos. Okay, E naught divided by 1 by omega C into cos of omega t. Can I write it like this? So I will be equal to E naught divided by 1 by omega C is how much? That I will call it as I naught. E naught by 1 by omega C, I'll call it as I naught. Listen, I'll be able to draw the phasor diagram only when they both are sine functions. Only when current and EMF both are either sine function or completely in terms of cos. So if you observe E, it is in terms of sine, whereas I is in terms of cos. So I need to convert it to sine format. So sine of what I will write as, it is omega t plus pi by 2. So I could have either written as sine of pi by 2 minus omega t or sine of pi by 2 plus omega t. But why did I choose the second one? Because I want omega t to be positive. That's what the input value tells me. So here also I want omega t to be positive. So I is equal to I naught into sine of omega t plus pi by 2. So when I draw the phasor diagram again, if I take this to be E, then it has rotated through an angle of omega t in the anti-clockwise. How I found omega t is in anti-clockwise direction? Because the angle is positive. Positive angle is in anti-clockwise direction, right? So this is x and this is y. Okay, 1 minute. I'll rub this. Listen. Now, if I have this to be I, right? Now this I is rotated through what angle? Through an angle of omega t plus pi by 2. It is going to stop here, right? When it is omega t plus pi by 2, this is going to be the value. This is pi by 2, and the whole angle will be omega t plus pi by 2. Then when I drop a perpendicular from here, this height will be I naught sine of omega t plus pi by 2, and this height will be E naught sine of omega t. Is that clear? understand what I did? We'll see that. So in this case, what I can observe and tell is current is leading the voltage by pi by 2, or voltage is lagging behind the current by pi by 2. What is this leading and lagging? I'll explain it slowly. You need to understand what I mean by that, by pi by 2. That we will see after we discuss power. Okay. Is that clear? So this happens in the case of capacitor. But this is a phasor diagram. For every such device, you need to draw a phasor diagram and a graphical representation as well. Again, a minute, 1 minute. It's not X and Y, it is again time, EMF, and current. Okay. So the graph for EMF is like this, where this height is E naught. Then what will happen to the current? Omega t plus pi by 2 means that current is leading the voltage by pi by 2. In the sense, the graph will get shifted to the left by pi by 2. Means the graph will start from here. It keeps going in this way. Because you think, no, if you want I to become 0, omega t should be equal to minus pi by 2. So the graph will actually start from here. So it will get shifted to the left. So what I can say is this value is E naught sine omega t, and this value is I naught sine of omega t plus pi by 2. Right. So what will be the third device? AC source across and inductor. We need to discuss about the AC source across and inductor. Let's say there is an inductor of length, inductor of inductance L that is connected across an EMF source of value E naught sine omega t. So current is flowing through it, right? So think of this logically. This current that is flowing through the inductor So I is alternating in nature. Is that right? When it is alternating in nature, then flux will change. When flux is changed, EMF is induced at the ends of inductor. And what do you call this EMF as? I'll call this as E dash. Okay. So what do you call this EMF as? Can I say E dash is equal to? I'll call it as back EMF. Since the circuit, is purely inductive. Okay, I repeat. Since the circuit is purely inductive, means there is only inductor, we can say resistance across the circuit is zero. Okay, because there is no resistor connected. So though the wire is bent in the form of a circle, though it has resistance, inductance will dominate the resistance. So we are saying resistance of the circuit is zero. In this scenario, what can happen is the input EMF will be equal to the back EMF. When input EMF is equal to the back EMF, what I can say is input EMF is E. This will be L into dA divided by dt. Why did I write L into dA by dt? That is the back EMF. That is the EMF induced across the inductor. But what is E? Is equal to L into dA divided by dt, which implies sine omega t into dt is equal to L divided by d naught into dA. Okay. Or I'll write it as E naught divided by L into dA. That makes more sense. So if you observe in every scenario, what is that we were trying to do? If input EMF is this much value, what is the corresponding current value? Right? So for that, I will be equal to integral of E naught by L into sine omega t dt. Can I write it like this? Yeah. So this will be equal to E naught divided by L into integral of sine omega t is minus cos omega t divided by omega. So this will be equal to E naught divided by omega L into minus cos omega t. Is that right? Oh, can I write this as E naught divided by L into minus of sine of pi by 2 minus omega t? No, omega else. Can I write the sine of pi by 2 minus omega t? But I have a minus sign also. I'm going to do something with it. Can I write it like this? So, can I say minus sine theta is equal to sine of minus theta? So, what I can do is I can push the minus sign inside. When I do this, I get E naught divided by omega L into sine of omega t minus pi by 2, which is equal to pi. Now I made omega positive. So what as you asked in the previous question, when will it be minus? Current lagging the voltage by pi by 2. So means if the EMF corresponds to the first quadrant, current will correspond to the fourth quadrant. When you draw the phasor diagram, you'll understand. But that option I don't have. E naught by omega it is. Right here. So proceeding with the next part. Actually, we have these are the basics. Okay. So if I draw a phasor diagram, there is a value of E, then it should stop at an angle of omega t. Then what about I? So this will be minus pi by 2. Correct? Right? Then how much will this angle be? Omega t minus pi. That omega t minus pi by 2 is the angle made by the current phasor with the x-axis in the clockwise direction. The first one, it is see that pi by 2 tells me it is lagging, current is lagging the voltage by pi by 2. So the angle between EMF and the current is supposed to be pi by 2. You add and see, no? Yeah. Omega t minus pi by 2 is equal to minus pi by 2 because clockwise direction. Oh, you're saying minus omega t plus pi by 2. See, it is actually pi by 2. No, that's simple. Magnitude of this, forget about this minus, okay. Maybe that minus is confused. This is pi by 2, accepted. So out of pi by 2, omega t is gone. So how much will this angle be? Pi by 2 minus omega t. But this is happening in the negative direction. So that is why I wrote it as omega t minus pi. Makes sense? Forget about the directions. This angle is omega t. This angle is pi by 2. Then how much is this angle? Pi by 2 minus omega t. Now this omega t is measured in anti-clockwise, so positive. This one is measured in clockwise, negative. So I put a minus here. Now this will be omega t minus pi. Okay. So if I drop a perpendicular from here, this will be E naught sine omega t. This will be I naught sine of omega t minus pi. Is that clear? Now, having said this, how is the graph going to be? Start from pi by 2. It will start in the negative direction. That's it. So this is the graph for what? Time. This is EMF and current. So if I drop a perpendicular, this height is E naught. Then where will I start from? So if it starts from here, observe. It is exactly upside down because so the phase difference is pi. So 180 degrees difference means out of phase. I naught sine of omega t minus pi by 2. This is E naught sine of omega. Right. The case of capacitor and the case of inductor, we saw one term. I is equal to E naught divided by 1 by omega c into sine of omega t plus pi by 2. And here I is equal to E naught divided by omega L into sine of omega t minus pi by 2. Right. So this 1 by omega c and here omega L have a name which are called as XC and this is called as XL. 1 by omega c. 1 by omega c is called as XC, which is called as capacitive reactance. So capacitive reactance is something similar to that of a resistance. But you don't call it as capacitive resistance, rather you call it as reactance. Okay. Similarly, XL is called as inductive reactance. Is that clear? So inductive capacitive reactance and inductive reactance. Now, can I say Xc is equal to 1 by omega c? Can I write it as 1 by 2 pi f into c? So I'm doing it simultaneously. Okay, observe so that. So X is equal to 1 by 2 pi f into c. For DC, F is 0. For direct current, frequency is 0. Yes, it doesn't change its direction generally. I'm not talking about fluctuating DC, I'm talking about the DC current. So then XC will become infinite. So what is the meaning of this? Means capacitor does not allow DC to pass through it. Means capacitor does not conduct direct current through it itself. Now comes an important question. In the second chapter, when we discussed capacitors, we were having all the diagrams with direct current. Direct batteries were supplying direct current. But if you see the important point there, we never discussed about what is the current it is allowing. We only discussed about what is the amount of charge it is able to put. Generally, in competitive exams, you get these kind of questions where resistor and capacitor will be connected in series. And if they are connected across a DC source, then what will happen is the current through the resistor will also be zero. Again, so if at all you have a circuit like this, resistor and capacitor, you get it in competitive exams like this. If it is connected across a DC source like this, if they ask you what is the current through this, answer will be 0 because they both are in series. Wherever series comes, current should be the same. So resistor, maybe it will allow, but capacitor will not allow DC to pass through it. So this will become like an open circuit. So there is no use of having this kind of a circuit. It will not work. Now the next important point is, I am able to observe that XC is inversely proportional to frequency. XC is inversely proportional to frequency. When you plot a graph between frequency and XC, the shape that you're going to get will be something like this, which is a rectangular hyperbola. Then what about omega L? So XL is equal to 2 pi F into L. So when you observe for DC, F is, so XL will be 0. So from this, what you can conclude is inductor will allow direct current to flow through it. That's what I told you in the previous chapter. So what is the job of an inductor? To oppose the rate of change of current. Because L is equal to what? E divided by di by dt. So L is inversely proportional to di by dt, means inductor will not allow the current to change with respect to time. Is that clear? Now when you try to plot a graph between XL and frequency, what will it look like? It will be a straight line like this. Okay. So this is all about what happens when you connect an AC source across a purely resistive circuit, purely capacitive circuit, and purely inductive circuit. Okay. So those who are online, I hope you could understand. Yeah?
Yes, sir.
Listen, if I take, okay, combination. If I take the combination of AC source connected across a series RC circuit. Okay. So this is R, this is C. Okay. Here I use the word series. So when I say series, what is constant? Current. Rate of flow. Or charge is flow. Charge doesn't flow. Okay. Whatever you want to say, no problem. Generally, in the case of resistor, you say it as current. In the case of capacitor, you call it as charge. But since here we are trying to find the relation between EMF and current, I use the word current. So when current is going to be constant, I want you all to concentrate. This is the trickiest part. Let us say this is the value of current which is flowing across the resistor. So in phasor diagram, I'm free to draw only current or only voltage also. Okay. If I say this is the value of current going through the resistor, then what can I say this value? What can I say this value is with respect to EMF across the resistor? So what is the first point I gave you? With respect to a resistor, EMF and current are in the same phase. Okay. When that is a scenario, I can say EMF is also in the same phase. Can I call this as ER? If this is IR. Now another important point to be noted is current across the resistor IR, and if I call the current across the capacitor as IC, can I say IR is equal to IC because I'm using the word series? Then, if IR is in this direction and IC is also in this direction, with respect to IR, how is ER? They both are in same phase. So ER will also be in the same phase. Whereas with respect to a capacitor, if current is IC, how is the voltage with respect to it? 5/2. Is it leading or lagging? Current leads, voltage lags. So current, if it is IC, then voltage will be EC. Am I clear with this point? This is the most important thing to be understood. So this is EC. I will draw it on the board. So I will call this as IR, IC. Now, EC will be lagging the voltage, lagging the current by 5/2. So can I say that this is EC? Right? So what I'm trying to say is ER and EC are perpendicular to each other, where EC is lagging ER by an angle of 5/2. Where did we get the idea from? We got the idea from current. So what are the steps to be followed? You need to first fix the direction of current. With respect to current, you should see how is the voltage across the resistor and how is the voltage across the capacitor. I hope this is clear. Now, ER is the voltage across the resistor. So can I call this as I into R? EC is the current across the capacitor. Can I call this as same I, but instead of R, I'll call it as XC. Okay. Now, this is a vector, this is a vector. Then how is the resultant going to be? And this resultant, I will call it as EZ. Okay, where this will be equal to I into something called as Z. I'll come to what that Z is. Okay. Now, what can I write? Actually, it is E effective. E effective na RMS value. So if I take E effective, this will be equal to root of ER square plus EC square. So what is E effective? I into Z will be equal to root of IR square is I into R the whole square plus IC square is I into XC the whole square. So IZ will be equal to I into root of R square plus XC square. I and I will get cancelled. Z will be equal to root of R square plus XC square, where the Z is called as impedance. Okay. So there are three terms that we have seen. One is called as resistance, second is called as reactance, and the third is called as impedance. So you use the word resistance when it is purely resistive. So resistance is the word used when the circuit is purely resistive. You use the word reactance when the circuit is purely capacitive or inductive. Okay, XC or XL. That is what reactance. You use the word Z when it is a combination of R and that is R and XC or XL or both also. That is when it is a combination of both resistive and reactive elements. We call it as impedance. XEC. You can do that. That's called rotation of axis. But that's right mathematically, but in your textbook they have given it like this. That is why I followed like this. What you told is not wrong. It's right. Diagram. Yes. The different ways of writing the same thing is Z will be equal to root of R square plus, in the place of XC, can I write it as 1 by omega C? So this is another way of writing. Okay. And secondly, if you see the angle between the effective resistance, sorry, effective EMF and the EMF across the resistor as phi, then what is tan phi equal to? EC divided by ER. With respect to phi, this is the opposite. This is adjacent. So tan phi is equal to, they both are perpendicular. This is X, this is Y. This is the, if this is phi, my Vishnu. Generally, phi is always taken with respect to resistor part only. Okay. So you take that as tan phi. So tan phi is opposite divided by adjacent. ER divided by, sorry, EC divided by ER. EC is how much? I into XC. ER is I into R. I and IR get cancelled. XC is 1 by omega C divided by R is R only. So this becomes 1 by omega CR. So tan phi is equal to 1 by omega times C into R. So that is the phase difference between the effective value and that of the resistance. Done. So this is all about an AC source connected across a series RC circuit. The next points that we are supposed to discuss is about RL circuit and LCR circuit, which we'll see in the next class. Two more classes I think will be done, not two, take 3 classes. But I hope you're able to understand it. So these are all the points we need to practice. So that's it from my side for today. So remaining topics we'll see it in the next class. So we'll wind up. Yeah. Those are online. I hope you could understand. Good. We'll wind up this.